Knowing some properties of expected values of random variables can make your life more interesting if you are into gaming. Of course, this is a conditional statement because I'm assuming that you want to bring math into something you're probably doing for entertainment and relaxation. But let's proceed anyway. So in the previous video, we looked at this bugbear attacking you for 2d8 plus 2 damage, and we made this big table, listed the probabilities, calculated the sum product of the outcomes and the probabilities. But there's actually a little bit faster way to do that. 1d8 has an average or expected value, man, what's wrong with me, of 4.5, and you can calculate that fairly simply, just like we did in the first expected value video. But so 2d8 plus 2 has an expected value of, well, if 1d8 is 4.5, then 2d8 would just be 2 times 4.5, and then add that 2 on the end. And if you do that, 2 times 4.5 is 9, plus 2 is 11, which is exactly what we got in the previous video, is 11. So you can apply this to a lot of different situations. Like this same bugbear has 5d8 plus 5 hit points, which is just another word for its health. So again, if 1d8 has an expected value of 5, so the total HP has an average of, so just do 5 times 4.5 plus 5, and what is this? 9, 18, 22 and a half, 27.5. Of course, bugbears can't really have 27.5, but you know, some of them have less than that, some have more, and it averages out to 27.5. So if you think about the distribution, though, how do we come up with a distribution for 5d8? Well, here it's pretty easy for 2 dice because we just put them in a table, but for 5 dice, we need first die, second die, and then 3 additional dimensions. So we can't really put it in a nice table form easily. Even like a young green dragon can exhale poisonous gas for 12d6 damage, which sounds like kind of a lot, and it is. So you might recall that 1d6 has an average of 3.5, so 12d6 has an average, again, average expected value, same thing, of 12 times 3.5, which works out to 42 damage, which is quite considerable. The ancient green dragons do even more damage. And you might think, okay, well, 42 is an average, and of course, if you make your what's called a saving throw, you only take half of however much is rolled. You can imagine if you're playing this game, someone actually has to roll 12 dice and add them all up, which is pretty, pretty comedic sometimes, with just dice going all over the place. But so if you think about the maximum, though, the maximum on 12d6 would be a 6 on every single die. That would be 72, but is incredibly unlikely because to get a maximum of 72, you'd have to get a 6 on every single die. So it'd be 1 in 6 to the 12th power. And if we calculate that, equals 1 divided by 6 to the 12th power, we get something that's incredibly tiny. It's not very likely this is going to do maximum damage. It's not very likely it's going to do minimum damage. If you want to come up with the distribution and say, okay, what is the probability it's going to do 41, 40, 39, all that stuff, how would you come up with that? Well, there is a formula. If we go here to Wolfram Math World, there's a formula up here developed, I think this is the reference, Uspensky in 1937, came up with this formula. The probability of getting a total of P on n dice with s sides each is given by this formula. Now, this formula is well beyond the scope of this class, but it is something you can calculate. You can put it in a computer program and come up with it fairly easily if you're into coding, and we haven't even talked about some of this notation. But the interesting thing when you look at the visualization is 1 die, all the numbers are equally likely. 2 dice, we saw this before, we get this triangular shape. 3 dice, though, we get kind of a curve. And 4 dice, hey, what is that? A wild normal distribution appeared. And if you use 5, 6, 7 dice, it would become even closer to the normal distribution. So the normal distribution comes up all over the place. But the point of this is if you're talking about something that does 12d6 damage, it's very likely to do very close to that average value and very unlikely to do close to the min or the max. How spread out are those values? Well, we can talk about standard deviation of a random variable for any of these situations or any other, and that's what we'll do in the next video.